Hi guys, welcome to our third video of the computer lab session for Dr. Preev's class. In last video we used ln function to fit the linear model and also use the summary function to report the regression result. And in this video we are going to, and from the regression result we can see that the coefficient estimate of the intercept and the excessive return of the market portfolio is slightly greater than 0 and slightly greater than 1 respectively. So in the context of the CAPM, like if the true population parameter of the intercept is greater than 0, we say that the risky security outperformed the market. And if the population parameter of the excessive return of the market portfolio is greater than 1, then we say that the risky security is an aggressive asset. So is it sufficient for us to conclude that the IBM is outperformed the market and also is an aggressive stock? The answer is we don't know, because the coefficient estimate are random variable itself. They are estimate of the true but unknown parameters, and hence they will, in a sense that they will actually vary from sample to sample. So just to illustrate, we will exclude one observation from the return data frame that we compute in the previous video, and then if we compare the regression result, we can see that the regression result will actually fluctuate, like even we just exclude one observations. So yeah. So in order to make any meaningful conclusion, we need to do some hypothesis testing. And for Dr. Preev's class, we're going to use p-value, and also please do not rely on the p-value compute reported by the default regression output, as they are based on student t distributions, and you're required to compute the standard normal distribution and use it to use the p-value computed from the standard normal distributions to make your conclusion. Okay. Actually, it is going to be. And actually, you're going to need the function pnorm, and as for any well-known distributions in R, like they have like they have 4 common actions, which is calculating the density, this cumulative distribution CDF, and quantile, and also a function to randomly generate the random variables for any well-known distributions, which is described by D, P, Q, R, and also with the name of the name of the distributions. And we will use pnorm to compute the p-value, as like it is, if the lower dot tail is equal to true, you will actually compute the CDF. But if we say it as false, then you will actually compute the survival function, which is the shaded area on the right tail. If we set it to lower dot tail equals to false. So in this case, so first of all, let's calculate the test statistics. Okay, we could for the p-value approach, we'll first we'll just name this the coefficient matrix as the coefficient. We just create an object name called this. And then as it's a matrix, so we could extract the element of the coefficient estimate of the intercept as the first row, first column, 1 before comma and 1 after comma, and the standard error, we can extract the standard error of the intercept as it is first row and second column. And then we set the hypothesized value equals to 0, and then we compute the test statistic. And if we actually print it out, and then it's actually the same as the t-value reported by our regression result. As by default, it also has it also set the hypothesized value equals to 0. But in the case that you have a non-zero hypothesized value, please do not rely on what I'll report, and you have to calculate your own. So yeah, we just calculate the test statistic, and then we will calculate the reject regions, the p-value on the right tail side. So first of all, we provide the absolute value of the test statistic as the first argument, and then we set the lower dot tail equals to false because we want to calculate the shaded area on the right tail, and then using the pnorm function, the pnorm function first argument as the absolute value of the test statistic, and set the lower dot tail equals to false. And we can explore the symmetric property of normal distributions, as the shaded area of the left tail is going to be the same as the right tail, so we just times 2, and it would be the p-value. And if we print it out again, we can see that it's 0.822356, which is greater than 0.05, and as it is way larger than any possible significance level, we would say that we cannot reject the null hypothesis that the intercept is equal to 0. In that case, we cannot say the IBM has abnormal return. And if you're interested in doing the using the test statistic approach, you can compute the critical value, say qnorm, and as it's a two-tailed test, it's going to be 2.5% for each side, so it's 97.5% threshold. And then you compute against the and then you compare against you use the absolute value of the test statistic compared with the 97.5% threshold, and then you get false, and therefore you cannot reject the null hypothesis, which is the same conclusion as the p-value approach.